In this section, we'll learn how to quickly compute characteristic polynomial of a given matrix. Quickly means in polylogarithmic time using circuits or parallel computer with polynomial number of processors. So we'll not consider a single-threaded model, a standard RAM model. We'll consider a parallel RAM model or Boolean circuits. We'll assume that we are given a matrix where the entries in this matrix are elements of some field. Maybe these are residues modulo some prime, maybe these are rationals. Anyway, we can encode them in binary form, and this is matrix of order n. And the characteristic polynomial of the matrix, which we'll denote by chi a of x, is the determinant of x times identity matrix minus a. So if we write that explicitly, we can see the following thing. So now if we expand these determinants into a polynomial, we see that the largest power of x is n, and we actually obtain it when we get the product of these guys on this transversal, the main diagonal of the matrix, and out of each of these terms we get x. So thus we get x to the power of n with coefficient 1. The coefficient of the power n minus 1 of x would be the following. So we again need to take all these guys, but now out of the product of these guys we take, out of all but one differences, we take x, and of one difference we take minus aii. So ultimately the coefficient which will gather near this guy is minus the sum of all the diagonal elements of matrix A, which is called the trace of the matrix A. But for now we do not really need that. We'll just say that it's minus some coefficient s1. Well, we can note that it's the trace of A, and so on. So let's denote the coefficients as plus s2 x to the power of n minus 2 minus s3 x to the power of n minus 3, and so on. The last coefficient would be minus 1 to the power of n times Sn. We see that this guy, the free term, is the value of the polynomial at 0, and if we plug x equal to 0 in here, we get just minus a. And the determinant of minus a is minus 1 to the power of n times the determinant of a. So we know that this coefficient Sn is actually the determinant of a. In many applications of matrices to, say, problems in graph theory, computing matrix determinants, inverse matrices, and other things like that is very important. And we'll learn how to compute all the coefficients of this characteristic polynomial quickly, and in particular, we'll learn how to compute the determinant of the matrix itself quickly as well. The algorithm would work for arbitrary field, be it the field of rationals or any finite field, and we'll now proceed with the algorithm. It would be convenient for us to deal with a different polynomial, not with the characteristic polynomial of a matrix, but rather with a polynomial x to the power of n chi of a of 1 over x. That is x to the power of n, the determinant of 1 over x times identity matrix minus a. And when we get x to the power of n into the determinant here, the thing under determinant is just multiplied by x. So this is the determinant of identity matrix minus x times a. So we'll deal with this guy, but when we actually expand this guy according to this form of the polynomial, we see that it's nothing but 1 minus s1 x plus s2 x squared, and so on, plus minus 1 to the power of n, Sn, x to the power of n. So we'll actually compute this guy, but anyway, its coefficients are just the same as the coefficients of the characteristic polynomial of A. We'll now denote the submatrices of A standing in these corners as A1, that's just 1 by 1 matrix, A2, and so on, where An is the matrix A itself. We are interested now in computing these determinants, which has just the same coefficients as the characteristic polynomial of A, and we'll denote this matrix by B. And just like we have introduced the submatrices of A, we'll introduce the submatrices of B. These would be symbolic matrices B1, B2, up to Bn. Now let's recall the Cramer's rule, that whenever we have a square matrix C, the elements of the inverse at the position I and j is equal to -1 to the power of I plus j times the ratio of the determinants, determinant of Cij bar divided by the determinant of C, where the determinant of Cij bar is actually the determinant of the matrix, which is obtained from the matrix C by striking out the ith row and the jth column. So this is the determinant of an n-1 by n-1 matrix. So each element of the inverse of C for any matrix C can be computed in this way. Now we see that in this notation, for every m, we have Bm 1, 1 bar, that is the matrix obtained from Bm by striking out the first row and the first column, is actually just Bm-1. And so Cramer's rule gives us that the elements of the matrix inverse to Bm in position 1, 1 is the ratio of the determinants. So it's the determinant of this guy, which is just Bm-1, divided by the determinant of Bm. Now that might seem a bit weird, because we probably have studied Cramer's rule for numeric matrices. And all these matrices, Bm-1, Bm, they are symbolic matrices, because B is defined like this. So the entries of matrix B are expressions of a variable x. But really that's fine. If we just treat all these entries of matrix B and of all other matrices that we'll further have as elements of the field of rational functions over F. So if our matrix A is a matrix with elements of some field of order n by n, then the elements of A and the elements of B and the determinants of these matrices, they all can be considered elements of the field of rational functions over F. What's that guy? The field of rational functions, which we can denote by f of x, is just the set of all the formal ratios of form p of x over q of x, where p and q are polynomials of x, and the polynomial that we have in the denominator is not identical 0. This is very close to how we construct rational numbers. Any rational number can be defined as a ratio of two integers. But when we define rational numbers, we treat some of the ratios as equivalent. That is, if one ratio gives the same proportion as the other one, then these are actually the same rational number. The same thing we have for definition of rational functions. So if we have two rational functions, p of x over q of x and p hat of x over q hat of x, we treat them as indistinguishable if the proportion is the same. If the product of the polynomials p times q hat is equal to the product of the polynomials p hat times q. And we clearly can define easily the standard arithmetic operations in this field of rational functions, just as we define the arithmetic operations on rational numbers. So now, if this guy is an element of f of x, and this guy is an element of f of x, then the ratio of them is also an element of the same field. And Cramer's rule can be considered even in case of symbolic matrices. So now, when we use this formula, we can obtain the following formula. If we multiply for m equal from 1 to n, we get the inverse matrix for Bn, the elements at position 1, 1, multiplied by the elements at position 1, 1 in the inverse matrix for Bn-1, multiplied, etc., by the element at position 1, 1 of the inverse matrix for B1 for the inverse matrix for B1, that's the product of these ratios. And this product would be telescoping because we have determinants of Bn minus 1 over the determinant of Bn multiplied by the determinant of Bn minus 2 by the determinants of Bn minus 1, and so on and so forth. So many things cancel out here, and in the end we get just 1 over determinant of Bn, and Bn is equal to B. So out of this formula we see that the determinant of B, the polynomial whose coefficients we are searching for, can be computed symbolically as follows. So if we take the inverse for both sides of this equation, we see that on the right side we'll have determinant of B, and on the left side we'll have this thing. So we'll now use this formula to compute the determinant of B eventually.